Okay, so our last video for chapter 14 is on basically a lot of cleaning up a lot of other things about gases. And the first one is the difference between a real gas and an ideal gas. You know, we called PV equals nRT the ideal gas law and didn't really say, well, what does that mean? So the ideal gas law is basically says pressure times volume equals N, the number of moles, times the gas constant times the temperature. But that's only true if you have an ideal gas. What is an ideal gas? An ideal gas is a gas that completely follows that kinetic molecular theory. So go back to chapter 13 and reread what the kinetic molecular theory is. Basically, the idea that gases are composed of small particles with no attractions between them that are very, very far apart. And there was two things in it that said, there were two tenets of the kinetic molecular theory that had the word negligible in them. And one was that the volume of the particles is negligible compared with the volume of the container that they're in. Remember, the word negligible means too small to make a difference. And so sometimes that is not true. Sometimes the volume of the particles is significant compared with the volume of their container. Well, when would that happen? If, for example, you are under high pressure. So the conditions where a gas is not ideal, the first one is under high pressure. And why is that? Because the volume of the gas is not negligible. Right? The volume of the gas is a larger fraction of the total volume. The second condition, or where gases is not ideal, or where a gas is not ideal, is at a low temperature. And when we mean low temperature, it's, we're pretty much, for most gases, we're talking pretty close to absolute zero. Why is that? One of the tenets of the kinetic molecular theory said that the attractive forces between the molecules was negligible. Okay, and the attractive forces are not negligible at a low temperature. Right? If I look at an ideal gas, there is no attraction between these two molecules. Right? They're moving so fast, they're so far apart from each other that there's no net attractive forces. But in reality, and especially if they're moving very slowly, which would be at a low temperature, there actually are some attractive forces there. And you can see how that plays out a little bit on this graph. So this graph is basically showing us that, that number 22.414, that 1 mole of gas has a volume of 22.414 liters at STP, right? And this is just showing you that that actually isn't necessarily true, especially, and look at the difference here, like chlorine actually is quite a bit off from ideal gas, whereas like helium is right on the nose. So what is the difference between the compounds or elements on the right hand of this graph versus the left? And basically, it's all about intermolecular forces. These guys have higher or stronger intermolecular forces. Because of that, these, especially the attractive forces one, they're more pronounced. Right? So a gas behaves more like an ideal gas the lower the intermolecular forces. Okay, another kind of thing to wrap up here is we've always so far just talked about one gas. So what will the pressure be if the volume and the temperature and the number of moles? What if there's a mixture of gases? And that's what the next section is all about. So first of all, we have this thing called Dalton's law of partial pressure. And what is partial pressure? Well, partial pressure is the pressure due to one gas in a mixture. So in this mixture of helium and nitrogen gas here, right? If I'm thinking about this being in a container, the total pressure is the total pressure exerted as these molecules collide with the walls of the container. And the total pressure, it really doesn't matter what is the identity of the molecules, right? But we know that the molecules of helium are colliding and the molecules of nitrogen are colliding. So the total pressure is always equal to the sum of the individual pressures. That's what Dalton's law of partial pressure is, that the total pressure is equal to the sum of all of the individual partial pressures. It is proportional to percentage. So, for example, the nitrogen in the air makes up 78% of the volume, and if we're at STP, if we're at standard pressure, which is 101.3 kPa, then 79.11 kPa, or 78.08% of that pressure, is due to the nitrogen. Okay. The next question, and this is how we would actually use this if we were going to do a lab on this. It says a mixture of oxygen gas, carbon dioxide, and nitrogen gas has a total pressure of 0.97 atm. What is the partial pressure of the oxygen gas? That's what this question is asking me to find. If the partial pressure of the carbon dioxide is 0.7 and the partial pressure of the nitrogen is 0.12. So just really, this is one where you kind of have to write the formula yourself. The total pressure would be the pressure due to the oxygen plus the pressure due to the carbon dioxide plus the pressure due to the nitrogen. We know that the total pressure is 0.97 atm. The pressure due to the oxygen is what I want to find. The pressure due to the carbon dioxide is 0.70. And the pressure due to the nitrogen gas is 0.12. So just subtract, and you get that the pressure due to the oxygen must have been equal to 0.15 atm. How does this actually, when would we actually use this? Well, we would do a lab where we would collect gas, and we would collect a gas over water, because if we just release gases into the classroom, there's no way for us to measure that gas. But if we do it underwater, we can actually measure what volume we would make. So what we would do is we would actually collect oxygen gas, and we would collect it underwater. The lab is performed at 22 degrees Celsius, and that's important. The total pressure in this big tube would be called a eudiometer tube. Okay, the total pressure in the eudiometer tube is 755.1 torr. Remember, torr is the same thing as a millimeter of mercury. And the question saying, what's the partial pressure of the oxygen gas? Right? Again, write the formula yourself. The total pressure is equal to the pressure of the oxygen gas, and because the gas is collected over water, there will be some water vapor in there. We know the total pressure is 755.1 torr, or millimeter of mercury. The question is asking, right, what is the partial pressure of the oxygen gas? And a table. This would be a table that we would easily have like in your lab packet. What is the vapor pressure of water at these different temperatures? And at 22 degrees Celsius, we know that the vapor pressure of water is 19.8 torr, or millimeter of mercury. So just subtract, and we would get that the pressure of the oxygen would be equal to 735.3 torr, same thing as a millimeter of mercury. And then the second part of this question would be if the eudiometer tube indicates the volume of the gas, How many moles of oxygen gas are in that sample? Well, the only formula that we have that has moles in it is PV equals nRT. I know the pressure of the oxygen gas is 735.3 millimeters of mercury. I know the volume. Now remember, this is in milliliters. I have to change it into liters. So 0.03563 liters. N would be the number of moles. The R is 62.36 liters times millimeters of mercury over moles times Kelvin. And the temperature would be 22 plus 273 or 295 Kelvin. And doing your division there, you would get 0.00142 moles of oxygen gas. Then we would do some stoichiometry, we would do all sorts of fun stuff with this in a lab. Okay, the last real concept in this chapter is Graham's law. And in Graham's law is, in general, at the same temp, so at a constant temp, the speed of the molecule is going to be proportional to the molar mass. So at constant temp, and remember that means constant average kinetic energy, right? Speed, how do I say this? As the speed, I don't want to say speed first. How about as molar mass increases, the speed of the molecules decreases. Look at this graph here, right? The x-axis is speed, and the y-axis is the fraction of molecules with that speed. So you can see oxygen here has a mass of 32.00 grams per mole, whereas hydrogen gas here is 2.016 grams per mole. Right? Smaller molecules, less massive molecules, are moving at a higher average speed. Right? The peak here would correspond to their average speed. And that sort of makes sense. Think about it in terms of football players. Right? The football players that move really quickly are not the largest players on the team. Right? They're not the linebackers there to block. The linebackers don't really move all that fast because they are more massive, literally have more mass. And this is going to help us with two concepts, diffusion and effusion. So what is diffusion? You learned about this in biology last year. Diffusion is the movement of one substance through another. Movement of one substance through another. Right? And going along with Graham's law, larger molecules would diffuse slower. Right? So diffusion, we often think about in biology class as being liquids or solutions, and yet really in chemistry, we can also think of it as being through gases, right? So here's just a picture of diffusion, right? And larger molecules will take longer to diffuse than smaller molecules. Effusion is probably one that you have not heard of before because effusion is very specific to chemistry and very specific to gases. It's the movement of a gas through a tiny hole. Movement of a gas through a tiny hole. This is the classic example of this is a balloon. Right, so you can see here, there's gas on the top of the cylinder. Here's the tiny hole. Only a small amount or number of molecules is actually going to be able to effuse. And of course, this follows Graham's law as well, that larger molecules effuse more slowly. Okay, there's a formula for this, and we'll go through and we'll do the mathematical formula for it in a moment. But just even take a look at this picture here, right? These are two balloons. This is like starting and this is ending. And so one is filled with helium and one is filled with nitrogen gas. Nitrogen gas would have a mass of 28.02, whereas helium is 4.003 grams per mole, right? So we would expect that after a certain amount of time that the helium, because it has a lower mass, would effuse quicker. And then, yeah, look, after 48 hours, the balloon is much smaller. The helium balloon is much smaller than the nitrogen balloon. In fact, the nitrogen balloon, it looks just about the same because those molecules are so massive, they have a hard time actually fitting through that hole. So the formula for the rate of effusion is kind of weird. It is rate 1 over rate 2 equals a big huge square root, and it's the molar mass of compound 2 over the molar mass of compound 1. And so this is where students get confused. It's very different than the formulas that we were using for like the gas laws, where it was like volume on top, volume on top. This is different compounds are actually like diagonal from each other. Okay, so we just want to really keep that in mind as we do problems 16 and 17, our last two problems in the chapter. So question 16 says, ammonia has a molar mass of 17.034 grams per mole, while hydrogen chloride has a molar mass of 36.458. If ammonia, this is all clues, right? If ammonia effuses at a rate of 3.50 moles per minute, that's literally how many moles go through that tiny hole in 1 minute, what rate will the hydrogen chloride effuse at, right? So we write our formula, and I just abbreviate like ours. Rate 1 over rate 2 equals big, huge square root, molar mass of compound 2 over molar mass of compound 1, making sure that, the same compounds are diagonal from each other. And then let's take a look here. If I want to solve for the rate will the hydrogen chloride effuse, it is always easier for me to solve for a variable in the numerator on the top. So I'm actually going to make the molecule number 1 the HCl. So that's what I'm trying to solve for, the rate of the HCl. So this will be the rate of the NH3, and then this will be the molar mass of NH3 over the molar mass of HCl. And now I start to plug everything in, right? The rate of the HCl over the rate of the NH3, that's 3.50 moles per minute, equals big, huge square root. The molar mass of the NH3, 17.034 grams per mole over 36.458 grams per mole. And then before we even do any math here, think about what it should be, right? HCl is a larger molecule, so its rate should be smaller. Okay, so do out the math now. These units completely cancel. So I literally, in my calculator, take 17.034 divided by 36.458, then take the square root of that. Then I multiply both sides by 3.50. So the rate of the HCl, L, is equal to, and three significant figures here, 2.39 moles per minute. Right? And it was smaller. The larger molecule effuses at a smaller rate. Okay, last problem. A sample of carbon dioxide effuses at 4.77 moles per minute. Under the same conditions, a noble gas effuses at a rate of 7.04 moles per minute. What is the likely identity of the noble gas? So how am I going to identify which noble gas is? Well, probably by its molar mass. Now, it's smaller. I shouldn't say smaller. The particle effuses, this unknown noble gas effuses at a quicker rate, which means it must have a mass that's lower than carbon dioxide. And if you look on a periodic table, helium, neon, and argon are the only three that have a mass that's lower than carbon dioxide. So it's going to be one of those three. So actually, let's do out the math and let's figure out which one, right? The rate 1 over rate 2 equals big, huge square root, right? Molar mass of compound 2 over molar mass of compound 1. And what do I want to solve for here? I want to solve for the molar mass of the unknown compound. So that's what I'm going to put there, which means chemical number 1, right, is going to be that CO2. So this will be the rate of CO2, and this will be the rate of that unknown compound. So now let's start plugging some things in. 4.77 moles per minute over 7.04 moles per minute equals big, huge square root. This molar mass of compound X, which I don't know, over the molar mass of carbon dioxide, which is 44.01 grams per mole. And now this is using your this is using your Algebra 2 skills. You know, when am I ever going to need to know this? Well, here it is. How are you going to solve for a variable inside a square root sign? Well, that's going to be to square both sides. Okay, so when I square both sides, then I'm able to, let's see, so 4.77 over 7.04 squared, and that equals the molar mass of compound X over 44.01 grams per mole, right? Divide, square it, multiply by 44.01, and you get 20.2 grams per mole is the molar mass of compound X, and that must mean it must be neon. Okay? So, what is your homework? Well, of course, your homework is the rest of the packet, right? And we're going to be doing some videos from this, so I'll be putting the video assignment together, and that will be up on Schoology as well.